In today's video, we're going to look at the law of cosines. So in our last couple of videos, we have been studying the law of sines, which gave us this equation that we could use in order to solve any triangle. The problem is that it can only be used to solve certain types of triangle. So they can be used when you have been given two angles and a side, or the case where you've got two sides and an angle that does not lie between them. So for the law of sines, it can be used first if we are given two angles and a side, or if we are given two sides and an angle that does not lie between those two sides. Okay. There are a couple other triangles that we can instead solve using the law of cosines. So the two different types that we are going to be able to solve using the law of cosines are first the one where we've got two sides and the angle is between the two sides of the triangle. So it's very similar to that second case for the law of sines, but this time the angle does lie between the two given sides. The other case that we will be able to solve using the law of cosines is when we have all three sides. The way that we denote these two cases is going to be side, angle, side, and side, side, side. So SSS and SAS. Okay. I'm going to show you how we get the law of cosines, and then I will go through the first case, the side angle side case. In the next video, we're going to look at the case where you're given three sides, and then we're going to look at some word problems. So first of all, we want to see what is the law of cosines and where does it come from. So let's say that you are given this triangle here, okay, and you have A, B, and C are the vertices, and you have alpha is going to be the angle down here. Now, because we have this triangle that doesn't necessarily have a right angle in it, what I'm going to do is I'm going to do kind of the same thing that I did when I proved the law of sines. I'm going to create a right angle because then I know more properties of my trig functions in order to solve something with this triangle. So I'm going to draw a line down the middle there that joins that vertex C to the line AB. So then I know that I have right angles either side of that line. Okay. Then I'm going to call this distance here, I'm going to call that H, and this distance here, I'm going to call that K. Okay. And then what I'm going to do is I'm going to take this triangle and I'm going to put it on the XY plane. So I'm going to take this triangle, I'll do this in green, and I'm going to put it in what we call standard position on the XY plane, which means that the bottom line of this triangle is going to lie on that positive x-axis, and then alpha is in standard position. So the terminal side of alpha is swept out from the positive x-axis through to wherever that terminal side is, that line AC. So that angle alpha is now in standard position from where we have put this triangle. Okay. What can I determine from this? Well, the first thing that I can determine is sine of alpha and cosine of alpha. I can look at this in terms of h and k, and also if I'm opposite this vertex B or the angle beta, I know that this side must have length B. So we're going to use that in this case here. So I can say that sine of alpha is always equal to opposite divided by the hypotenuse, which is h over b. And then I know cosine of alpha is always adjacent divided by hypotenuse, which would be k over b. So by creating that right triangle there, I can look at sine and cosine of alpha in terms of these new h and k's that I've put in thanks to that right triangle. I can then rearrange this and say that h is equal to b sine alpha and k is equal to b cosine alpha. Now what I'm going to do here is I'm going to use the distance formula like we did in our previous law of sines proof. And I'm going to look at that point B there. What's its coordinates? Well, the length of this whole side here is C, okay? I'm opposite the angle gamma or the vertex uppercase C. So I know that that length is C. So what I can do here is I can say, okay, the coordinates of that point B are going to be C0 because I am in standard position, that alpha is in standard position, which means that the x coordinate of B is going to be C, the length of that line AB, and it sits on the x-axis, so its y-coordinate is 0. Now, what's this coordinate of this point C here? Okay. Well, we've just worked that out, okay? Its x-coordinate is k, its y-coordinate is h. So I know that this has coordinates b cosine alpha and b sine alpha. Okay, so now I'm going to use my distance formula between these 2 points here, B and C. Okay. Now that distance I know is going to be denoted by A. It's the side that is opposite alpha, so it's going to have length A. So that tells me, using my distance formula, that A is going to be the square root of the difference between the x coordinates squared plus the difference between the y coordinates squared. So it's going to be C minus B cosine alpha squared plus 0 minus B sine alpha squared. I'm just using that distance formula. So now, if I square both sides, I'll get rid of that square root. So that leaves me with C minus B cosine alpha squared. And then I've got plus 0 minus B sine alpha squared. So that's going to give me negative B sine alpha all squared, which is going to be plus B squared sine squared alpha. Okay, so I can already simplify that part. Now I've got to multiply this out. That's going to give me C squared minus 2BC cosine alpha plus B squared cosine squared alpha, and then I've still got that B squared sine squared alpha. I could do some simplifying here, okay? If I combine these two terms and take out that common factor of B squared, I'm left with B squared, and then I have sine squared alpha plus cosine squared alpha. Well, that's one of our trigonometric identities. This thing here just equals 1. So I've got 1 times B squared is just B squared. So I get B squared plus C squared minus 2BC cosine alpha. And that's A squared. This is the law of cosines. Okay. One side, we'll call it A squared, is equal to each of the other two sides squared minus 2 times the other two sides multiplied together, multiplied by cosine of the angle that is opposite this side. Okay. It doesn't matter which way around A, B, and C are. By that, I mean we could say that A squared is equal to B squared plus C squared minus 2BC. Because it doesn't matter which way I put my triangle and how I label it, it doesn't matter where my A's, B's, and C's sit. So I can also say that B squared is equal to A squared plus C squared minus 2AC cosine of beta, which is, again, this angle is opposite this side. And C squared is equal to A squared plus B squared minus 2AB cosine of gamma. Okay, so it works for all of your sides and each of your angles. Just make sure that the side you have here is opposite the angle that you have here, and the two sides here are going to be the other two sides from what we have here. Okay, so just make sure that you keep that in mind. But like I said, it does not matter how you actually label this triangle, it's going to work either way. If you actually had a triangle that had a right angle in it, so if we had a triangle that had a 90-degree angle in it, what does this do to this formula? Well, let's say that you labeled your 90-degree angle as alpha. Okay, cosine of 90 degrees is just going to be 0. Okay, cosine of 90 degrees, think about it on a unit circle, it's going to be the x-coordinate of that point on the unit circle on the terminal side of 90 degrees. The x-coordinate there is 0. Okay, so that would actually completely eliminate this term in that case. So when you have a triangle that has a 90-degree angle in it, you're just left with this, which is just Pythagoras, which is exactly what we have used before. That's where that comes from. Okay, so keep that in mind. If you do end up seeing a 90-degree angle, that's where it comes from. Okay. What I'm actually going to do first is go ahead and look at an example where we are given all three sides. I'll do the side angle side example in the next video, but we'll start with the example where you are given all three sides. So in this example, we have this triangle here. I've got A, B, and C, and then alpha, beta, and gamma. And then my sides are going to be 5, 6, and 8. And I'm going to use the law of cosines in order to solve this. What I will say is, when you have an example like this, what I want you to do is use the law of cosines at the start, but then you can actually use the law of sines in order to finish the problem off. So kind of keep that in mind, and you'll see that as we go through this. So using my law of cosines, and you can figure out which one that you want to use here, doesn't really matter either way, you're going to at least end up with one angle out of this. Okay, I'm going to use c squared is equal to a squared plus b squared minus 2ab cosine gamma. And like I said, you could do the a squared plus b squared version like I have here, or you could start looking for a squared and have b squared plus c squared. It doesn't matter which version of this you use. I'm just going for this one, and I'll find gamma first, but you could go ahead and use one of the other forms and find alpha or beta. Okay. So in this case, c is going to be the length that is opposite to gamma, so that's going to be h squared. Then a is 5, and we're squaring that, and b is 6. And then a times b is going to be 30, multiplied by 2 is going to be 60. cosine, and we don't know what gamma is yet. So I've got 64. Then this is 25 plus 36, which will give me 61, minus 60 cosine gamma. Okay. And if you rearrange this, you should find that cosine gamma is equal to negative 1 over 20, or if you want to write it this way, negative 0.05. Okay. Then if I do cosine inverse of this, I find that gamma is equal to 92.866 degrees. Okay. Now we know that because this is greater than 90 degrees, my other two angles must be less than 90 degrees. Okay, so keep that in mind, especially when we now go ahead and use the law of sines. There must be only one possible triangle here because this thing's greater than 90 degrees. So now when I go ahead and use my law of sines, I'm only looking for one particular triangle. Okay. So I now know gamma. So I'm going to use that and say that sine of gamma, 92.866 degrees, divided by my side C, which was 8, is equal to, now you can go ahead and do this for either one. You have A and you have B. We'll start with A. So I know that A is 5, so I'm going to have sine of alpha over 5. Then by plugging this into a calculator, you find sine of 92.866 degrees. You divide that by 8 and then multiply by 5, and that should give you that sine of alpha is equal to 0.6242. So when you do sine inverse here, alpha is going to equal 38.625 degrees. Like I said, we only have to worry about one triangle here, okay? I don't have to worry about, like we did in our previous video, with 180 minus this and looking at a second option for a triangle. I know that there must only be one triangle here because this gamma is already greater than 90 degrees, okay? And now I found alpha, beta's easy to find. I can just take my two angles, add them together and subtract from 180. Okay. And when you do that, you should end up with beta is equal to 48.509. Okay. So I now have, I started out with all three sides, I now have all three angles as well. So how did I do this, just as a recap? We took our triangle, we used the law of cosines, okay? And you can use any one of these sides to find any one of the angles. It doesn't matter whether you solve for alpha, beta, or gamma. Okay, you just pick one. I solved for gamma. Once I've solved for gamma, I then looked at the law of sines and used the law of sines in order to solve another angle, just because it's easier to use and it means that I don't have to go through the law of cosines again. It's just an easier way of doing it. You can, by all means, if you wanted to, just use another form of the law of cosines here and find a second angle, and then do 180 minus those two angles, and that will give you the third angle. You can by all means do that. It's just this way is a lot more complicated than just using the law of sines. So I've used the law of cosines in order to find one angle, and then once I have that one angle, I can then go ahead and use my law of sines to find another angle. And then I've just done 180 minus those two angles. It gives me my final angle. Like I said, okay, you will have to check whether there is more than one possible triangle here. I knew from the angle that I solved for, because this was greater than 90 degrees, there was only one possible triangle, okay? Because I don't have any other angle that could be greater than 90 degrees here, okay? So I know that I'm not looking for a second possible angle when I find this alpha here, okay? But if I had a smaller angle here for gamma, I may have to check that alpha and do 180 minus that angle to see if that other angle would fit into my triangle. But in this case, I don't have to do that. So do use our things that we did in the last video in order to see if you do need that second triangle. But like I said, we don't need that here. In the next video, I will go over the side angle side examples, and then we will look at some word problems that incorporate all of this law of cosines and law of sines together.